Okay, so YOLO finishes here. Now I'll start with my last example. One thing is left. This is your face expression part. In the face expression, I'm hoping that you have trained your model. So I did performed here training my algorithm. Uh, Yesterday it finished. So I'll just show you how what are the additional things you need to add into it so that you can particularly make the overall predictions. This is for face expression. Okay, so in the face expression, we have not added. Again, the same thing. You have to start reading from the top to to the line where the model has trained or started training itself. That particular line you need to skip. Like I have executed till summary and I have read where my model, the trained model is stored or saved, and these are my logs. I'll not execute the history. So once your history is executed, you have saved your algorithm performances in this md .hdf5. After that, you don't have to repeat these things again. Now let's go to the next part where we will try to use model dot load underscore weights, and we start with my e open cv. Okay, it says, what does it says? Says it is not compatible. But okay, sorry, it is. Of course, it is not compatible. It is basically used as mask expression model. Okay, I have loaded the weights. You have to add additional things. Let me make the changes. Did you finish training this particular model, right? Face expression. So you can skip the history line. Don't run it again because the saved model is already getting stored in this particular location as a .hdf5. So you can use it any day to make predictions. So I'll use this saved model to make recognition. So recognizing image data here, we'll take your image underscore new, which is given by cv2.imread, p open cv, face expression, face expression images, train. I'm taking one of the angry faces, which is let's say 22.jpg. Now we'll try to show it. plt.im show. This is a grayscale image underscore new. That's an angry face. You can see it. Now we need to make changes here according to our requirement. So image new will be equals to cv2.resize with my image new, and this has to be resized to a new shape of 64 cross 64. What is my input image? 64 cross 64 cross 3. Here we have reshaped it to 64 cross 64. Let's pick my image new dot shape. Then we go here with my blue, green, red, cv2 dot split. with my image new. Next, with my image new dot equals to cv2 dot merge red, green, blue. X new equals to np dot squeeze. Now, to understand what a squeeze will do, look at here the output of the image new, or in fact, look at the shape. When you will do the squeeze, this is gonna be image new again, and you will observe x underscore new dot shape. So no changes you can see, right? So what it will do here is, if you will just try to observe the data, which is coming up like your RGB format, we took it, and after applying this, you are easily able to observe it here that your images now looks like an array. Looks like there is no need. It's already 64 cross 64 cross 3. Okay. One thing we have to definitely apply on this, and that will be related to, I think this is not required. Okay. Because it's not changing the shape. So let's try to pick here my image new. Let's say X new. This will be needed. That is, we need to make all the pixels. There is image new dot as a type. We have to make it as float 32 type, and we need to divide your all the new value by 255. After doing this, we will pick here my X new, which will be reshaped. We have to reshape it as 1 cross 64 cross 64 cross 3. And we need to make prediction model.predict, and we need to pass here x underscore new, which will return me the. Now you can see that this is a example code for uh, multi-class classification, and multi-class classification gives priority for all the classes. That's why np.argmax was needed, so that we can find the label index position of the maximum value. So it is predicting as 0. And what is 0? 0 stands for angry. So it's a correct prediction. Similarly, you can try on the different images as well. You can also try it on the video as well. I'll write the code for that. Remember that I'm just following the same thing as we did in our previous examples, how to prepare the data for my model. So I did nothing but we ensure that the input shape matches with the model shape. In all these cases, if you observe while building the model, we kept the input shape as 64 cross 64 cross 3. So this does look like a grayscale image, but it is not. It is a colored image. Okay, it's a black and white image, you can say. Just like the way we made a algorithm which was enough to predict a mask. We need this time 7 different categories for these 7 different for predicting correctly the 7 different. Hey, wait. What is the name? Mask expression. Oh, mask expression. That's obviously a wrong name I have taken, but yeah, that's how the things work. Okay, let me copy all this code. Okay, now give some expressions, and you will easily able to see few expressions. It can show 5 to 6 five type of expressions. It will able to show correctly. Make an angry face like this. It will make it angry. Angry, it will able to predict correctly. Fear, it will able to predict correctly. Happy, it will able to predict correctly. Sad, it will able to predict correctly. Surprise, it will able to make. So model accuracy is very low, right? That's why. And that's not due to the model's inefficiency, that is due to the data's inefficiency. Five expressions it will able to detect properly. For that you have to show the expressions as per the images available in your data set. So see the expressions, and you have to show angry, fear, happy, sad, and surprise. These five predictions it can do correct. Five expressions it will able to predict. Disgust and neutral are hard to detect. Neutral face is very difficult because you have to be, very much good in giving the expression. So others it will able to detect. Angry, disgust, sorry, angry, fear, happy, sad, and surprise. Now you're able to see it. So first of all, try to understand that until now we were doing the classification. Now we will segment. Like I wanted to find out the shaded region of the person, where the person is. I wanted to shade the region where the bicycle is. I wanted to shade the background. I wanted to shade if a person is having a tumor, so where exactly, how much region is the tumor region. I wanted to shade that. So these all things comes under the semantic segmentation part. We have majorly classification, object detection, and segmentation. These are the three popular things that we do. Okay, classification we have understood that it can be done through CNN. Object detection we have learned that it can be done through or achievable through the YOLO. And now it's time for the segment. Especially in terms of your biomedical images, segmentation is very important because it will basically will try to through the medical images it will we will able to understand that what are the shaded region where the tumor lies or the affected region is, like not only tumor but it can detect other things as well, like if somebody is having uh, let's say pneumonia, so we will able to detect the region in the lungs x-ray, that where exactly the affected region is, like we have a cough or not, so what portion of the lungs are affected and what portion of the lungs are still not affected. So in order to do that, in order to achieve, we are having an algorithm which is of U shape, and it's called as your segment. Sorry, it is known as your unit algorithm. Due to the shape, it is known as a unit, of course. In our given example, we will apply here the particular part of MRI segmentation. We will do it. Okay, and also you can perform here the classification and segmentation both. If wanted to do the both, you can do both as well. If you wanted to do the simple classification, you can do the classification as well. But we need to read the images first to prepare on everything. We need to rely on our model, and we need to create a model first. And after preparation of the algorithm, we will talk about how unit can be used to build our segmentation part, and to perform the segmentation we have to build the algorithm again. So let's get started with our example code. You can do this on Google Colab as well, because it takes a lot of time to get trained. The Google Colab will be, in order to work on the Google Colab, you need to upload these images on Google Drive, and from the Google Drive you can basically read the image. Okay, so according to this, this is how accordingly it will work. We will perform here tumor segmentation part, and let's try to learn about it, and let's try to understand that how it will work properly. Okay, so let's get started. First, we will apply. Let's import the library. Import pandas as PD. Import numpy as NP. Import cborn as SNS. Import matplotlib dot pyplot as plt. Import cv2 from skimage. Import input output from ipynb, sorry, ipython dot image, sorry, dot display. Import display. Import os. Import random. Import glob. Taken, so there is no need to describe about the classification, but here the description will be needed because of one simple reason, and that is these are medical images, and medical images are not read in the way that we have been doing the things as of now. Let me show you. When you will unzip these images, it will look like this. Let me take here my brain MRI. Okay, so you can see and observe here that we have got data, brain MRI, and MRI segmentation. This is how each patient details are given to us. These are my MRI, and this black is my masked image. Okay, if we have got the tumor, we have got the mask of the tumor. Where exactly is the region? How much is the region? These are all displayed here. You can see. Okay, if there is no tumor detected, it is black. The tumor region is masked as white. This is how my data is available to us. This is my data. Now look at here. This data does not have any label, right? We don't have any label, and we don't have any details about these except if you will scroll down and you will find data.csv. This is where my data details are available. So the preparation of a medical image starts from this. You will always find some CSV files like .csv and something, and this particular CSV file that you observe here, this will be responsible for preparing the patient details. So we have the details like you can see we are having some labels like RNA sequence cluster. Like these are obviously the medical terminology, whether the person has died or not, ethnicity, race, etc. Gender is there, tumor location is there, tumor tissue site is there. These are not important. What is important here is the patient details. So every patient details are available, and for every patient details, you are having the multiple images. These are all patient IDs. Okay, that's how every medical images will actually look like. So what you will do is you will start using pandas library. That's why you can see that though it is a medical data, but I have to prepare it using pandas. So pd.read underscore csv, and I need to provide the location, which is E. So my location is brain MRI segmentation. That's where my location is present. So there are some null values in this as well. Total number of elements are 110 entries are there. Total 110 entries are available here. Let's pick my brain data frame dot head. Will display me the details. Obviously, the patient and all these details are available, but we are not interested in taking up these. We are interested in reading the path of the images where my images are available. So what I'll do is I will start reading it using for subdirectory. Variable name can be anything in glob.glob. This is just to read each and every file from the available path, and we will provide here the path which is available to us from this location. Okay, multiple folders will be there here, and I'll concatenate it with a star. That means it can be all. So we will read all the files and all the. This is just to read. Okay, like if I'll print here, putting up a colon. If I'll print here the subdirectory, you will see that it is gonna just it is reading all the folders and all the files. It's reading all the folders, all the subpath, and are getting printed, right? So we'll use this subdirectory, but there is a catch in this. We don't have to read the subdirectory, but we have to read the individual images which are present in all these subdirectories as well. So in order to do that, we will write here directory name, which is equals to subdirectory dot split dot subdirectory path. Let's name it as subdirectory path dot split. Take it as forward slash. Take all the value as -1 for file name in os dot list directory subdirectory path colon image path equals to subdirectory path plus forward slash plus file name data map dot extend directory name image path. Now you see that we are getting some error here in this case because there are some unusual path as well, like .csv and all. That is not a directory and all. We need to remove it. So this program needs to be put under a exceptional handling part. Reason is very simple, that we have to omit out some of the portion or some of the part which is not playing an important role. I mean that particular part has to be omitted basically. So that's the reason why we'll put it under try, and yeah, let's go ahead with my exception as e. So we are handling these exception. What are these exceptions? Those images which does not data map is not defined. Let's define the data map then. Data underscore map list. Okay, so these are my data which are now stored under data map, if you will, if you wanted to see it. So I'm hoping that you have understood what is under subdirectory, and these are the two exceptions data sets which are omitted. They are not part of it. But what is inside a data map? Data map inside, we have got path till all the TIFF images. What is TIFF extensions are your medical images. Two extensions are there, remember it. There are two extensions. There are two most common medical image extensions. What are those? .tiff and anyone? .dicom. These are your two most frequent. They are not gonna be .jpg or something, but they will be .tiff or .dicom. So we just read all the images. Now we will put that part under the available brain data frame. That's what we will be doing next. So this part is all about creating the path, and that's where this glob has played its role. And why we have to print the exception? Don't print it. This line is for reading only directory path. Okay, now it's time to take on the data frame, and let's prepare it. This is my patient ID, and we'll start taking it as I of all for I in data underscore map, and we take here all value, skipping the last two element. Sorry, up to two decimal, up to skipping every alternative value. Why we are skipping alternative value? Because you can see the both the images have the same name. Look at here. This is your image. This is mask. 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 So colon 2 will ensure that the step size is not every next value, but it will be every alternative value. So that's what we wanted. We wanted to take these as your first images path, and then later we will start reading it from this, which will be your mask path. So two things are there. You take here patient ID with my for loop, and it starts from here and it goes to my path. This is my image path here. Let's go with path with my data underscore map. We'll start with 1 colon 2 again. Okay, so patient ID, let's see what we have got. So patient ID we have got, which is your normal image, but if you will observe here, we are not getting the exact, we are not getting the patient ID, but rather than that, we are also getting this MRI hyphen segmentation and all, right? Which is stored, of course, in your data map part. Okay, and so we need to try to skip that part. We have to skip this MRI dash segmentation, and that we can simply do it with the help of what is a slash I have used here. It's a forward slash. Here also it's a forward slash, but why then it is showing me readme.md like this? This is not a directory. That's fine, but something is wrong. One second, let me try again. We take here my forward slashes with my MRI segmentation plus all, and okay, so it takes here this. No, something is wrong. Let's talk about data map 0. Why this MRI segmentation is coming? Okay, inside the MRI segmentation, are we having any other MRI segmentation? No. This is E data brain MRI dash segmentation, and then it should be able to read only this, which is my patient ID. Try to pick again data map for subdirectory path in globe.glob. It will return you all the paths. Try directory name subdirectory path dot splitted by. Okay, let's do one thing. Let's skip how many values we are about to get in this case. So let's try to get the count. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Let's do one thing in this case. Let's slice this data and let's start from the index position 17. Now I think we'll get it. Okay. Just add one more line here in the end. Instead of starting from zero index, we have to omit out few portion because see, the patient ID should be available here, not the extra value. The path is taken here. Let's try to read the path so that you can see what is inside a path actually. df path, and let's add a 0. So this is the TIFF path that we are taking. If you will take 0, that's your first image. Then you can see that it does not contain any masked images. It is only containing your image. It's not containing the TIFF, masked image. Displays path to MRI scan image. Remember, there is a mask image as well. Hope you have made one small update here. If you will not make an update, it will give you error. Please make an update in this one that I already updated in your Google snipper link. And why we are doing it? Because when we did the split, it is not reading the ID, but it is reading the some extra MRI segmentation portion as well, which we don't want to include here. Now that's the correct one. No? This is how the path should appear. Just compare. This is how I am getting. Now next, let's get the base length of the image. Sorry, path. Base length equals to, we get here base length, which is given by len of, I'm reading this 83, or you can also write it like this. So the base length is basically the total size, which will vary from your path, like how your path has been taken. So don't look for that it value is matching or not. You just write the correct code and you will get the proper base length. Now we need to this particular thing, we need to add the mask path as well, and we need to also order my data in a random order so that different patient IDs are shuffled. Okay, we don't want them to be available in a sequence. We want it to be available in a random format. These are all part of your data preparation, guys, which will remain common for other medical images as well. Of course, you need to apply the logic there. Like I found the path is not reading correctly, so I added to start from 18th, 17th index position so that I will able to read only the patient ID details and other details will be omitted. Start with my import random data frame images is equals to data frame not df str contains. So we have got here my details. df underscore masks path dot str contains mask. Okay, understand. Read images from data frame that we just created df. Read images path from data frame which does not contain mask in it, which does not contain mask in it. And now read the images path from data frame which contain or which have mask in it. Base length equals to base length, some other variables. and image length, which is equals to 4. And why it is 4, you can see that it is coming out to be dot tiff and mask length, which will be 9. So these are basically the total unwanted part which we don't need, like mask contains this in the end, that's total 9 character, and whereas the end image length contains 4 character, which is dot tiff. Data sorting, images equals to sorted data frame images, path or values, e equals to lambda x colon. I take here x value with my base underscore length. Let's perform here sorting check with indexes equals to random dot random integer starts with my 0 length of images minus 1. Okay, so here we are basically trying to take the random indexes, and that will come through the total length of the images minus 1. You know that it starts from 0, so the last value will be not considered. That's why we will go till the second last position. We'll get all the indexes. Why second last? Because last and second last, they have the same patient ID, remember. uh, so we need to take it till that particular position, and we need to start sorting it. Apart from this, if you will look at here, we have written something like the image length, the end portion of the image length, that is the extension part. If you will see, we have got dot tiff here in this case, and we have got underscore mask dot tiff here, and we have sorted them. Path to the start with my images and index, path to the mask. So we got here my details of, and we converted everything into brain data frame. These can be also considered as your positive and negative diagnosis. Diagnosis contains my mask path colon value, which is equals to np dot max cv2 dot im read mask underscore path. Start with my if value is greater than 0, return 1, else return 0. Okay, so we are gonna label my images. Wherever mask is found, it will be labeled as 1. If mask is not there, it will be labeled as 0. That is what simply we are trying to do. Okay, so if mask path is found, it will be 1, otherwise it's 0. So only for masked images it will be labeled as 1, otherwise it is labeled as 0. That's what this function is doing. I'll write it here. Label mask images as 1. So data preparation is quite a tedious work. You can see it that we have to go through a lot of processing of the data. But that is how all the other images will also be working. We go with my mask, and let's add the label to my existing data frame that we are building. Mask path. To that we will apply lambda x colon cause negative diagnosis of value x brain data frame. Thing is wrong. What's wrong in this? Mask underscore path is not defined, but it is defined here. Mask underscore path. Mask. That's okay. We have images with mask, no? There are two type of images. Remember, I talked about. One is the black and white. That is a mask image. This is your original image. This is your mask image. It's return here mask. That's what we are reading. Mask.tiff. This is again simple normal image. This is mask image. This is
So
normal
how
image.
do
This is
we
mask
read
image.
this mask image? Matlab, how we have done this black?
It is auto. It is a data part of the data set.
Okay, that's what I wanted to understand.
This is available as a part of the data set.
Because if we are getting MRI scan, then that is the full MRI image, and masked image they have made in their data set.
Correct. In order to do this type of images, you need to basically do the edge
Contrast
detection,
type of thing.
contours.
Okay.
You have to do the contours and you need to fill those regions with white and rest all regions with black.
Because it will require another. Um, matlab, we have to prepare this type.
Yes. You have to prepare it, but in this case, we are already having this data set already had the masked part, so we don't need it. Okay, so we got here my image path and the mask path and the labels. These are my random patient IDs that has been sorted. Total number of images are 3929. That's my final details. Here it should return this type of path first, forward and backward, no problem. And then patient IDs we are taking. Just verify that you are getting in every stages the same output or not. Though this is a dynamic code, so you can see that we are getting here path to the image, path to the mask. So we have prepared the data frame. The final data frame with labels are ready. Okay, let's display these images. plt.im show, tv2.im read, and brain data frame dot mask label mask path, and take the image number 2, which is coming out to be like this. On contrary, if I wanted to display simple path, we have got mask path and we have got what image path. So let's pick here image path with the same index. Okay, this is your mask path. This is the image path. You can see the tumor region and the highlighted black region as well. In order to display multiple images, let's just display 12 masked images counted as 0. This is a normal subplotting. tld.subplots. The shape of the subplot is 5 cross 3 cross fixed size. 20 cross 50, that's the shape. For I in range of length to brain data frame, if brain data frame mask I. Let's compare this with 1, and let's take that the count is smaller than 5. Okay, read masked color image and display img equals to input output dot im read brain data frame dot image path of I. So we have read the image. I will be some random images as I have said that I'll take it some set of the images, and we wanted to take here those images where the mask is 1, and the overall images that we will take should be smaller than 5. That means we will generate total 5 index 1 0 1 2 3 4. That's why the count is smaller than 5. Basically these are all so we will display only those images where the mask is 1. That means the label of the data frame that we will be displaying will be only those images where which are these type of images. Once we got it, and we will display only 5. Now let's take here axis count 0 dot title dot set underscore text brain MRI ax count 0 dot im show display mask in grayscale mask equals to input output dot im read brain data frame dot mask underscore path of I. Let's pick here count of 1, set these as mask color map equals to gray. Okay, display everything. Figure dot type underscore layout. So we will be getting here our 12. Sorry, we will be getting here two type of images right now. One will be the original mask image and the relevant black and white image of the mask portion. So after doing it, we will be ready to prepare our algorithm. In fact, let's read all the data set first. So we will use it to prepare our data, and then we will use our algorithm to start training this data set or this algorithm. In fact, it is taking so much time. We need one more thing here, and that is basically we'll replace here white region with red color over original MRI image. Compare mask as 255, and let's fill it with the red color. Okay, so you can see that basically what we did here is that whichever the region was there, we made it filled with red color so that you can see that where my tumor lies. To a simple plotting that we have done earlier as well. You're simply doing IM show to display the images. One is in the grayscale, the other one is a colored MRI image. This one is interesting because here we are comparing that in the mask where is white color, right? We are comparing marks equals to 255, and that particular 255 is filled with red color, which is 255 comma 0. Brain underscore data frame dot train equals to brain underscore df dot drop columns equals to patient ID, train data frame train. Okay, we got here my mask, mask dot apply with lambda x of str. Got here my info. We have got here image path. We have got here mask path, and we have got here mask details, which will be my details. Okay. Now let's split my data. Patient ID, we have dropped it. The role of patient ID is no more required. We're just checking that it is dropped, and then we are checking our info of the labels and everything. And now it's the simple. Now in this case, we don't have the separate train and test data, so we have to split the data by using scikit-learn package. Split data, train and test from sklearn dot model underscore selection, import train test split, train and test, use the function train test split, pass here brain data frame underscore train data. In this case, we will take the test size as 15%, as the data size is very large, so that we can quickly do it. Image data. A lot of images are there, so 15% also seems to be a very large number of testing data. We are getting almost like 500 testing data and 2839 trained data, which belongs to two classes. One labeled as training data set and the other labeled as test validation. Class mode is taken as categorical here, so this that's why we are getting two classes. You can replace categorical by binary as well. At the same time, we have to also apply the testing generator as well, which will be test data. From the train data, we have got around 50. We have taken this for validation as well as training, and the testing data is already separate here. This is your train data, this is your test data. The same training data we have taken, we have passed here, and from there we are taking some around 15% of the data, which will go to the validation from the train data itself. Because we have written here validation is split, so 15% from the training data will go to 15% from training data that goes to validation of model. In this case, we will be using a simple concept of ResNet 50, which is basically part of a transfer learning model. Let me tell you what is transfer learning. Keras application. If you will look for the Keras application, there are some. That's the difference between Google and all this. Hmm. If you will look at here, this particular link, you will find that there are the Keras package not only help to create your algorithm or model from the scratch, but also this helps you to build or import some of the available algorithms which are already been trained for some similar type of problem statement, but not the same, but similar type. Let's say classification or segmentation or these type of things it has already gone through and it has trained. So the advantage that we get is that we don't have to train the model from the beginning, but it is already a trained model and we have to start training it for our new sample data. So the advantage is that in this part or in this section, your algorithm, two advantages. One, as I said, that algorithm will already have some loaded weights. So it will start training from that loaded weight and it will finish. Second thing is that the algorithm will have some data sets present in it. Sorry, the algorithm as it is already trained, so you don't have to create from the scratch, but it is already an existing algorithm which you can directly import, so you don't have to think about how many number of neurons or how many number of layers we should have. These are already predefined. You can choose according to your application that whether you wanted to use VGG16, VGG or RESTnet 50 or Inception V3. These are the available options that you have and you can choose it accordingly. And this example, these application list keep on increasing. So transfer learning is a very important and very important part, which is useful in deep learning to in a two-way. Like as I said, you will be having already available models, and we have to directly use it. And let's get. So I'll be using here base. Here we are using ResNet 50. Weights will be ImageNet. It is always ImageNet only. Load knowledge or transfer of knowledge. Transfer of knowledge, which is nothing but it is transfer of weights. That's why it is called as transfer learning, right? Whatever it has learned, it is saved under ImageNet. Default, input shape will be equals to 256 cross 256 cross 3. This is your base model, which will take some time to get imported if you're doing it for the first time. Base model dot summary. That's my model summary here. Base model equals to ResNet 50. Weights equals to ImageNet. Include top equals to false. I just wrote here so that I can show you that what is the summary here. Same I need to copy here. No? To start with my input layer, model equals to sequential model dot add convolution 2D filters equals to 3 kernel size equals to 3 cross 3 pairing equals to same activation function equals to rectified linear unit input shape equals to 256 cross 256 add transfer learning model dot add base model. So basically we have to first define my base model, which is your ResNet 50. And in order to define it, you will always provide the weights first, which will be fixed to ImageNet. It will be always ImageNet, no matter if you are using ResNet 50 or any one of these. Include top will be false because the first layer will be this. And you need to define your input shape. Just add this transfer learning model to your existing model. And then after this, you can do the same thing as we did in our other examples. Similar to that, model.x. Only difference is that we are using average pooling here. You can replace it by max pooling, no problem. Batch normalization is new entry. This is just to avoid the overfitting of the model. That's your fully connected neural network. And because in this case I have used categorical, so we have to prepare it like a multi-class classification, though it is a binary class. Adam we already know. Loss function, which will be again categorical cross entropy, Adam optimizer, and your model will be ready. So nothing new. Only two things you need to remember, that whenever you are using a transfer learning, you have to first define it as a base model, and you need to define one of this type of layer where you will define filter as a number of depth. This will be three only. Don't increase this. Kernel size, very minimum value, and input shape, which will be of course the shape of your image, and then add the transfer learning details with average pooling. Flatten your data set. Again, batch normalization to ensure that your model is not overfitted. This is your fully connected neural network. This time we are using two layer. The last layer is could be confusing, that it is a binary class, but I'm using units equals to 2 and activation equals to softmax. So that is just because the details that we have written here are similar to your multi-class classification. Then we have provided here loss value, etc. Details are written. Here is my dataset, train underscore generator. This is my training data. Validation data, which will be equals to valid underscore generator. Epochs equals to 30. Shuffle true, callbacks, verbose equals to 1. Okay. Model will start getting trained. It will take some time because the model is number one, the model is very dense here, so that's the reason why I took a little bit extra session, so that you can see that it takes a lot of time. uh, just make sure that you finishes the training. When how many epochs we are having? 30, around 30 epochs are there. So I'll train these models. You can see that it is taking almost around close to 50 minutes, but of course this is the first layer, so it will take the maximum time. After this, the duration will definitely drop. Maybe you can expect 30 minutes for each epoch. That means around 15 hours of training is required here. That's where the model that we are saving will be useful. Brain data frame, where is brain data frame? Where? These are all dynamic code. Why you have written like this patient ID and all? Where you are stuck?
Because it
Here.
was not, it was showing that
No,
all arrays must be of the same length.
no, 1 second. These are all dynamic code. You don't have to make any changes here. I'm already taking. If this path is correct, then this code will work for whatever the path you have taken. So first verify this. That's why I was asking whether you are getting it correctly or not. If you are getting it correctly, then this way these are all
This,
dynamic code. Where I'm using,
this
I'm
was
not
the
using
path:
anywhere.
content drive, my drive, MRI segmentation, TCGA,
How
DU6
I will
post.
able to understand it, ma'am, 1 second. It is possible for me to hear and understand that whether it is correct or not.
I'm not
I don't
getting
think
these
so, right?
two backslashes type of thing.
That's okay. That doesn't matter. Are you getting the path till TIFF? That is what my question is.
Yes, I'm getting the path till TIFF. But then also it's
Then it
showing
will work.
all arrays
Then
must
it
be
will
of the.
work.
Okay, I'll check. Then I'll get
Then it
back.
will work. We have got base length here. Just try to get the base length and it will work.
Base length is
Because where
95.
I'm here, whatever it is there, number is doesn't. That's why this is dynamic, right? I'm not using anywhere my path. You see that anywhere I'm using path? No,
No.
I'm using all the variables. So what I'll do is I'll upload this code until here, and you all try to run it on wherever you are running correctly, so that we should be ready for our last. I think 1 hour. I just said hardly it will take to build to discuss about the unit thing. This example is just one more thing and it will be finished. But yeah, I wanted to start the this part so that the algorithm should finish its training of the model. And yeah, let me share this code and the other codes as well. MRI classification and segmentation. So one more day, but it will be not the full day. We will have like 1 hour or so. What happened? It is not around 1 hour of session will be more, just to finish rest of the things. Face expression.
Yes, tomorrow will be the last day of the session. Unfortunately, I won't be able to join that session tomorrow, so I'll see the recordings. But thing is, I have few queries, and now it's too late actually to talk on those. So, is there any possibility that you are going to have you will be answering queries through the WhatsApp group that we have or no?
Yeah, the training and the testing part correctly. The code is uploaded, guys. You can check your code properly and check the path. This is a link. Verify and see if you can sort out your issues. The problem will be not in the coding part, but it will be in your path and all. So try to go through it once again. I've written most of the comments, so you can read the comments to understand the coding part as well. Because this is a little complicated. I mean, not very much as that, but the problem here is that we need to prepare the data. Our images are not ready, so it's all about pandas and data preparation part. Sometimes we need to do it in this way as well. Just wanted to show you. Once my model will be trained, we will able to analyze the accuracies and all everything tomorrow.